Experimental design. The learning objectives for this section are 1. Explain the difference between subjects and within subjects experiments. List some of the pros and cons of each approach. And decide which approach to use to answer a particular research question. 2. Define random assignment, distinguish it from random sampling, and explain its purpose in experimental research and use some simple strategies to implement it. 3. Define several types of carryover effect, give examples of each, and explain how counterbalancing helps to deal with them. In this section, we look at some different ways to design an experiment. The primary distinction we'll make is between approaches in which each participant experiences one level of the independent variable and approaches in which each participant experiences all levels of the independent variable. The former, where they experience only one level, are called between subjects experiments, and the latter, where they experience all levels, are called within subjects experiments. Between subjects experiments. In a between subjects experiment, each participant is tested in only one condition. For example, a researcher with a sample of 100 university students might assign half of them to write about a traumatic event and the other half to write about a neutral event. Or a researcher with a sample of 60 people with severe agoraphobia, the fear of open spaces, might assign 20 of them to receive each of 3 different treatments for that disorder. It's essential in a between subjects experiment that the researcher assigns participants to conditions so that the different groups are, on average, highly similar to each other. Those in a trauma condition and a neutral condition, for example, should include a similar proportion of women and men, and they should have similar average IQs, similar average levels of motivation, similar average numbers of health problems, and so on. This matching is a matter of controlling these extraneous participant variables across conditions so that they don't become confounding variables. Random assignment. The primary way that researchers accomplish this kind of control of extraneous variables across conditions is called random assignment, which means using a random process to decide which participants are tested in which conditions. Do not confuse random assignment with random sampling. Random sampling is a method for selecting a sample from a population, and it's rarely used in psychological research. Random assignment, however, is a method for assigning participants in a sample to the different conditions once you have those participants, and it's an important element of all experimental research in psychology and other fields too. In its strictest sense, random assignment should meet 2 criteria. One is that each participant has an equal chance of being assigned to each condition. So for example, a 50% chance of being assigned to each of 2 conditions. The second is that each participant is assigned to a condition independently of other participants. Thus, one way to assign participants to 2 conditions would be to flip a coin for each one. If the coin lands heads, the participant is assigned to condition A. If it lands tails, the participant is assigned to condition B. For 3 conditions, you could use a computer to generate a random number from 1 to 3 for each participant. If the number is 1, they get condition A. If it's 2, they get condition B. If it's 3, they get condition C. In practice, a full sequence of conditions, one for each participant expected to be in the experiment, is usually created ahead of time, and then each new participant is assigned to the next condition in the sequence as they're tested. When the procedure is computerized, the computer program often handles the random assignment. One problem with coin flipping and other strict procedures for random assignment is that they're likely to result in unequal sample sizes in the different conditions. Unequal sample sizes are generally not a serious problem, and you should never throw away data that you've already collected to achieve equal sample sizes. However, for a fixed number of participants, it's statistically most efficient to divide them into equal-sized groups. It's standard practice, therefore, to use a kind of modified random assignment that keeps the number of participants in each group as similar as possible. One approach is block randomization. In block randomization, all the conditions occur once in the sequence before any of them is repeated. Then they all occur again before any of them is repeated again. So within each of these blocks, the conditions occur in a random order. Again, the sequence of conditions is usually generated before any participants are tested, and each new participant is assigned to just the next condition in the sequence. The table in the textbook and the one shown here, the image, show such a sequence for assigning 9 participants to 3 conditions. The Research Randomizer website, or randomizer.org, will generate block randomization sequences for any number of participants and conditions. Again, when the procedure is computerized, the computer program often handles the block randomization. Random assignment is not guaranteed to control all extraneous variables across conditions, however. The process is random, so it's always possible that just by chance, the participants in one condition might turn out to be substantially older, less tired, more motivated, or less depressed on average than the participants in another condition. However, there are some reasons that this possibility is not a major concern. One is that random assignment works better than one might expect, especially for large samples. Another is that the inferential statistics that researchers use to decide whether a difference between groups reflects a real difference in the population takes the fallibility of random assignment into account. Yet another reason is that even if random assignment does result in a confounding variable and therefore produces misleading results, that confound is likely to be detected when the experiment is replicated. The upshot is that random assignment to conditions, although not infallible in terms of controlling extraneous variables, is always considered a strength of a research design. Matched groups. An alternative to simple random assignment of participants to conditions is the use of a matched groups design. Using this design, participants in the various conditions are matched on the dependent variable or some extraneous variables prior to the manipulation of the independent variable. This guarantees that these variables will not be confounded across the experimental conditions. For example, if we want to determine whether expressive writing affects people's health, then we would start by measuring various health-related variables in our prospective research participants. We could then use that information to rank order participants according to how healthy or unhealthy they are. Next, the 2 healthiest participants would be randomly assigned to complete different conditions. So one would be randomly assigned to the traumatic experiences writing condition, and the other would be assigned to the neutral writing condition. Then the next 2 healthiest participants would be randomly assigned to complete the 2 different conditions, and so on, until the 2 least healthy participants are assigned. This method would ensure that participants in the traumatic experiences writing condition are matched to participants in the neutral writing condition with respect to health at the beginning of the study. If, at the end of the experiment, a difference in health was detected across the 2 conditions, then we would know that it's due to the writing manipulation and not to pre-existing differences in health. Within subjects experiments. In a within subjects experiment, each participant is tested under all conditions. Consider an experiment on the effect of a defendant's physical attractiveness on judgments of his guilt. Again, in a between subjects experiment, one group of participants would be shown an attractive defendant and asked to judge his guilt, and another group of participants would be shown an unattractive defendant and asked to judge his guilt. In a within subjects experiment, however, the same group of participants would judge the guilt of both an attractive and an unattractive defendant. The primary advantage of this approach is that it provides maximum control of extraneous participant variables. Participants in all conditions have the same mean IQ, same socioeconomic status, same number of siblings, and so on, because they're the same people. Within subjects experiments also make it possible to use statistical procedures that remove the effect of these extraneous participant variables on the dependent variable, and therefore make the data less noisy and the effect of the independent variable easier to detect. We'll look more closely at this idea later in the book. However, not all experiments can use a within subjects design, nor would it be desirable to do so. carryover effects, and counterbalancing. The primary disadvantage of within subjects designs is that they can result in order effects. An order effect occurs when participants' responses in the various conditions are affected by the order of conditions to which they were exposed. One type of order effect is a carryover effect. A carryover effect is an effect of being tested in one condition on participants' behavior in later conditions. One type of carryover effect is a practice effect, where participants perform a task better in later conditions simply because they've had a chance to practice it. Another type is a fatigue effect, where participants perform a task worse in later conditions because they become tired or bored. Being tested in one condition can also change how participants perceive stimuli or interpret their task in later conditions. This type of effect is called a context effect or a contrast effect sometimes. For example, an average-looking defendant might be judged more harshly when participants have just judged an attractive defendant than when they've just judged an unattractive defendant. Within subjects' experiments also make it easier for participants to guess the hypothesis. For example, a participant who is asked to judge the guilt of an attractive defendant and then asked to judge the guilt of an unattractive defendant is likely to guess that the hypothesis is that defendant attractiveness affects judgments of guilt. This knowledge could lead the participant to judge the unattractive defendant more harshly because he thinks that's what he's expected to do. Or it could make participants judge the two defendants more similarly in an effort to be fair. Carryover effects can be interesting in their own right. For example, does the attractiveness of one person depend on the attractiveness of other people they've seen recently? But when they're not the focus of the research, carryover effects can be problematic. Imagine, for example, that participants judge the guilt of an attractive defendant and then judge the guilt of an unattractive defendant. If they judge the unattractive defendant more harshly, this might be because of his unattractiveness. But it could be instead that they judge him more harshly because they're becoming bored or tired. In other words, the order of the conditions is a confounding variable. The attractive condition is always the first condition, and the unattractive condition the second. Thus, any difference between the conditions in terms of the dependent variable could be caused by the order of the conditions rather than the independent variable itself. There's a solution to the problem of order effects, however, that can be used in many situations. It is counterbalancing, which means testing different participants in different orders. The best method of counterbalancing is complete counterbalancing, in which an equal number of participants complete each possible order of conditions. For example, half the participants would be tested in the attractive defendant condition, followed by the unattractive defendant condition, while the other half would be tested in the unattractive condition first, followed by the attractive condition. With 3 conditions, there would be 6 different orders: ABC, ACB, BAC, BCA, CAB, and CBA. So some participants would be tested in each of the 6 orders. With 4 conditions, there would be 24 different orders. With 5 conditions, there would be 120 possible orders. With counterbalancing, participants are assigned to orders randomly, using the techniques we've already discussed. Thus, random assignment plays an important role in within subjects' designs, just as in between subjects' designs. Here, instead of randomly assigning to conditions, they're randomly assigned to different orders of conditions. In fact, it can be safely said that if a study does not involve random assignment in one form or another, it's not an experiment. A more efficient way of counterbalancing is through a Latin square design, which randomizes through having equal rows and columns. For example, if you have 4 treatments, you must have 4 versions. Like a Sudoku puzzle, no treatment can repeat in a row or a column. For 4 versions of 4 treatments, the Latin square design would look like the one shown on the screen. You can see in the diagram above that the square has been constructed to ensure that each condition appears at each ordinal position, meaning A appears first once, second once, third once, and fourth once. and each condition precedes and follows each other condition one time. A Latin square for an experiment with 6 conditions would be 6 by 6 in dimension. One for 8 conditions would be 8 by 8 in dimension, and so on. So while complete counterbalancing of 6 conditions would require 720 orders, a Latin square would only require 6 orders. Finally, when the number of conditions is large, experiments can use random counterbalancing, in which the order of the conditions is just randomly determined for each participant. Using this technique, every possible order of conditions is determined, and then one of these orders is randomly selected for each participant. This is not as powerful a technique as complete counterbalancing or partial counterbalancing using a Latin squares design. Use of random counterbalancing will result in more random error, but if order effects are likely to be small and the number of conditions is large, it's an option available to researchers. There are 2 ways to think about what counterbalancing accomplishes. One is that it controls the order of conditions, so it's no longer a confounding variable. Instead of the attractive condition always being first and unattractive always being second, the attractive condition comes first for some participants and second for others. Likewise, the attractive condition comes first for some participants and second for others. Thus, any overall difference in the dependent variable between the 2 conditions cannot have been caused by the order of conditions. A second way to think about what counterbalancing accomplishes is that if there are carryover effects, it makes it possible to detect them. One can analyze the data separately for each order to see whether it had an effect, for example. When 9 is larger than 221. Researcher Michael Birnbaum has argued that the lack of context provided by between subjects designs is often a bigger problem than the context effects created by within subjects designs. To demonstrate this problem, he asked participants to rate 2 numbers on how large they were on a scale of 1 to 10, where 1 was very, very small and 10 was very, very large. One group of participants were asked to rate the number 9, and another group was asked to rate the number 221. Participants in this between subjects design gave the number 9 a mean rating of 5.13 and the number 221 a mean rating of 3.10. In other words, they rated 9 as larger than 221. According to Birnbaum, this difference is because participants spontaneously compared 9 with other 1-digit numbers, in which case it is relatively large, and compared 221 with other 3-digit numbers, in which case it's relatively small. Simultaneous within subjects designs. So far, we've discussed an approach to within subjects designs in which participants are tested in one condition at a time. There's another approach, however, that's often used when participants make multiple responses in each condition. Imagine, for example, that participants judge the guilt of 10 attractive defendants and 10 unattractive defendants. Instead of having people make judgments about all 10 defendants of one type, followed by all 10 defendants of the other type, the researcher could present all 20 defendants in a sequence that mixes the 2 types. The researcher could then compute each participant's mean rating for each type of defendant. Or imagine an experiment designed to see whether people with social anxiety disorder remember negative adjectives like stupid and incompetent better than positive ones like happy and productive. The researcher could have participants study a single list that includes both kinds of words and then have them try to recall as many words as possible. The researcher could then count the number of each type of word that was recalled. Between subjects or within subjects. Almost every experiment can be conducted using either a between subjects design or a within subjects design. This possibility means that researchers must choose between the 2 approaches based on their relative merits for the particular situation. Between subjects experiments have the advantage of being conceptually simpler and requiring less testing time per participant. They also avoid carryover effects without the need for counterbalancing. Within subjects experiments have the advantage of controlling extraneous participant variables, which generally reduces noise in the data and makes it easier to detect any effect of the independent variable on the dependent variable. Within subjects experiments also require fewer participants than between subjects experiments to detect an effect of the same size. A good rule of thumb, then, is that if it's possible to conduct a within subjects experiment with proper counterbalancing in the time that's available per participant, and you have no serious concerns about carryover effects, then that design is probably the best option. If a within subjects design would be difficult or impossible to carry out, then you should consider a between subjects design instead. For example, if you were testing participants in a doctor's waiting room or shoppers in line at a grocery store, you might not have enough time to test each participant in all conditions and therefore would opt for between subjects design. Or imagine you're trying to reduce people's level of prejudice by having them interact with someone of another race. A within subjects design with counterbalancing would require testing some participants in the treatment condition first and then in a control condition. But if the treatment works and reduces people's level of prejudice, then they would no longer be suitable for testing in the control condition. This difficulty is true for many designs that involve a treatment meant to produce long term change in participants' behavior, such as studies testing the effectiveness of psychotherapy. Clearly, a between subjects design would be necessary here. Remember also that using one type of design does not preclude using the other type in a different study. There's no reason that a researcher could not use both a between subjects design and a within subjects design to answer the same research question. In fact, professional researchers often take exactly this type of mixed methods approach.